In this video, we're going to start adding the strong base to our uh, weak acid. So this part of the titration, we're going to see what happens as we begin to add the base, and we have to compare the moles we start with to the moles of base added. So the first thing we need to do in these steps is we need to take the liters, 0.04 liters of our HA, and we need to multiply it by the concentration because 0.150 moles over 1 liter would give us the moles of HA. And what we get here would be 0.0060 moles. And then what we have to do is the same thing for the KOH. So this is the moles of the HA. The KOH, we are taking 0.030 liters because we have to convert the milliliters to liters. And we're going to multiply that by the concentration, 0.100 moles per 1 liter. And what we get is 0.0030 moles OH minus. OH minus is just the base that is present in KOH. And what happens our reaction is our HA is going to react with OH minus to give us H2O and A minus. And so we are not at the equivalence point yet. So we can use Henderson-Hasselbalch. All we have to do is see that if we do our kind of rice sort of table-ish, it's not really a rice table because it's no equilibrium, it's just, I guess, an addition or a subtraction table. If we start with our 0.006 moles here, 0.003 moles there, and none of this, what's going to happen, I'm going to erase this portion down here. What's going to happen is we're going to completely consume the base because it's our limiting reagent, and this is not an equilibrium. So I just subtract the base from the left side, and I'm going to add HA because for every base I consume, I produce one A minus. So I'm going to add A minus over there. And what we get is 0.003 moles of HA, no hydroxide, and 0.003 of A minus. And we can plug this into our Henderson-Hasselbalch equation, in which pH equals pKa plus the log of A minus over HA. This point is called halfway to the equivalence point because we added half the amount of base as we have acid. And what's special about that is when you take A minus and divide it by HA, 0.003 divided by 0.003, you get 1. And the log of 1 is always going to be 0. So in this scenario, pH equals pKa. Now, keep in mind, these technically are supposed to be concentration values, but we don't have to convert our moles back to concentration because they're in the same solution. So I would just divide them by the same number, and that number will get removed when we divide and make our ratio anyway. So for the Henderson-Hasselbalch only, when you do pH calculations, you can be just in moles and not in concentration. Whenever you solve for pH using negative log of H plus, or whenever we use the rice table equilibrium, Ka equals x squared over concentration, those have to be in concentration. But only for the Henderson-Hasselbalch can you keep it in the number of moles. And so for this one, pH equals pKa. So just in your calculator there, you can find the pKa by taking the negative log of the Ka, which is 9.8 times 10 to the negative fifth. And what we get is a pH of 4.01. So that is how we solve before we get to the equivalence point. If you know you're at the halfway to the equivalence point, you can just take pH equals pKa. If you're not at the halfway point, we have to actually do the math a little bit more, and we'll see that in the next example when we add 50 milliliters.